Hi, this is the second assembly language lecture about digital logic, and we're going to look at the transistor and how transistors are like switches and how you can use switches to make logical operators like NAND gates, etc. A semiconductor is a material that's kind of conductive and kind of not, in between conductors and insulators, and the foundation for pretty much all of our solid-state devices these days, and they're found in this part of the periodic table right here, right down here. Silicon, germanium, and those kind of things are semiconductors. And transistor was discovered, or maybe I should say dreamed up by some scientists at Bell Labs back in 1945. They found that you could take a semiconductor, which inherently, if it's pure, doesn't conduct, and if you put some p-type dopant, basically an element very similar to the semiconductor, but having one less electron, that would make it so that it appeared to have current conduction with positive charges. And you can do a similar thing with picking the next row over in the periodic table, and that makes it an N kind of dopant. And if you put a few purities of the N-type material into the silicon, it makes it conduct, and it conducts with electrons. So you could, by doing that selectively, you can pick whether the current conductor is negative or positive, and that was kind of the trick for making semiconductor transistors. So basically what they did is they used these semiconductor materials that were doped to make switches that were either on or off, and you could switch it on or switch it off by attaching a voltage to a control pin. So digital computers use a lot of these transistors. The kind of transistors that are used nowadays are MOSFETs. Back in my day, there was the Intel 4004 with an amazing 2,300 transistors, and now the i7 has 730 million transistors. It's incredible. So if you look at how the density has changed as a function of time, you come up with something called Moore's Law, and it just doubles every 1.5 to 2 years. So now we're going to look at the metal oxide semiconductor transistor. Like I said, a transistor conducts current when it's on, and it doesn't conduct current when it's off. That's just like a switch. So this is a schematic symbol for an N-type MOSFET. There's a gate over here on the left, and basically what happens when you put a positive charge on the gate, it attracts negative electrons right along the channel here and makes a channel where current can flow down through the device. But if you don't put the positive electron or the positive charge on the gate, it doesn't attract the negative charges, and then current doesn't flow. It's like a switch. Basically, when you put a positive voltage on the gate, it turns the switch on. So if you put 0 volts on the gate, the switch is open. That's like off. And if you put 3.3 volts on the gate, it's closed. It's like on. There's a p-type transistor, which is very analogous to the n-type transistor, except you switch the n-type dopant with the p-type dopant. And so what happens when you put a negative voltage or a low voltage on the gate here, it will cause holes or positive carriers to move up next to the gate here, and it makes current flow. When you put a positive voltage on here, then it scares those holes away and no current flows. So it's like a switch, only it's basically, notice when this one was on, this one is off. So if you put a positive voltage on this one right here, it turns it off. If you put a negative voltage or a 0 voltage on it, it turns it on. So here's the story. You put 0 volts on, it's closed. 3.3 volts on, it's open. So these are complementary devices. Notice one is kind of the mirror of the other. And these are called metal oxide semiconductor transistors, or actually when you use both of them together, they're complementary metal oxide semiconductor transistors, and that's what we usually do, use them together. And so it's usually CMOS is the type of technology you see that's used in computers. Complementary metal oxide transistors, or CMOS gates, are made up by putting one of the N-type MOSFETs underneath a P-type MOSFET. So the idea is that you want to make this a switch here, which is open when the switch here is closed, and there's a switch here. When the switch here is open, you want to make that one closed. So you put an N-type device here and a P-type device there, and this will give you what's known as an inverter. So this is the C for complementary in the CMOS. Either this switch is closed on the bottom, or the switch on the top is closed. Okay, so let's look at the inverter here. The inverter basically, if you put a 1 in, it gives you a 0 out, and those kind of ideas. Okay, so let's look and see what happens here. So here's a schematic of an inverter. We have a PMOS device upstairs and an NMOS device downstairs. So let's see what happens if you put a high on the input, and this is 3.3 volts here. Put 3.3 volts there. It's going to turn off this device and turn on that device, which gives you a low out. So that's what you got, a low out here. If you put a low in, a 0 in, what it does is turns on the high device, because there's a high voltage across here, which makes the P channel here, and allows it to conduct, and current flows from there to the output, making it a 1. So notice if you put a 1 in, you got a 0 out. If you put a 0 in, you got a 1 out. So that's the inverter. That's the NOT gate. There's this truth table for the NOT gate. And truth table basically lists all the inputs, all the possible inputs, and gives the outputs for those inputs. It's a really handy way of showing what something is accomplishing in a logic world. This thing right here is the schematic diagram for an inverter. It's an abstraction. It really inside, they've got these kind of things, and of course these are also abstractions for physical device, that's made up of a piece of semiconductor chip. Okay, how do we make a NOR gate, or a NOT OR gate? Well, what you do is you hook 2 of these P devices in series and 2 N devices in parallel, and you get a NOT OR gate. So if these guys are both 0, what happens? Well, it turns on both of those transistors, which allows it to conduct to from the high 3.3 volts to make the output 3.3 volts, or 1 is on the output. In any other configuration, one of those guys is off, and one of them is on the bottom instead of being off like this, and so then you end up with a 0 on the output, and that's the truth table for a NOR gate. And here is the schematic for a NOR gate, the symbol. And so how do you build an OR gate? We want an OR gate, not a NOR gate. Well, what you do is you start out with a NOR gate, like that, and you put an inverter on the end, and then you've got a NOT NOR gate, which is an OR gate. So there's your OR gate, and your truth table, and your symbol. Notice it doesn't have the bubble on the front. The bubble indicates a NOT operation. You can almost see that here as well. So how do we make a NAND gate? Well, what we did was we switched, these 2 switches are in series, so both of them have to be on to make it low, and either one of these on will make it high, and that gives you a NAND gate, a NOT AND gate. And here's what happens if you put 1s in. You'll get both of the ones on the bottom on. Any other configuration, you're going to get one of the top ones on and one of the bottom ones off at least. So there's the truth table for the NAND gate. Here's the symbol for the NAND gate. Notice the little bubble for the not AND. So how do we make an AND gate? Well, you're probably catching on here. We start out with a NAND gate, and we add an inverter. And there you have it. There's the truth table. We've got our AND operation. And notice this looks just like the symbol for the NAND gate, except there's no bubble in front. So, what would happen if we took two complementary logic outputs, CMOS outputs, and we hooked them to a bus? A bus is a bunch of connections here, all going to the same wire. So this CMOS output says, I want the bus to be low. This guy says, I want the bus to be high, and this guy says, I want the bus to be high, and there's going to be a short directly from the battery right here over here to there, and it's going to draw a tremendous amount of current until it burns something up. There's the current. So one of them, there's an argument about who's going to win, and as they say, lets the magic smoke out. So what you need is a tri-state driver, or you can use pull-up resistors to do that. So these are tri-state drivers, and basically the way it works is that with this pull-up resistor right here, if any one of these guys pulls it to ground, this will be the bus will be ground. If all of them are open, in other words, all the switches are off, then the resistor here will pull it up to 3.3 volts. So it's kind of any one of them can turn make the thing go low. In some ways, it's kind of like a wired OR gate. And here is the schematic symbol for this tri-state buffer. Okay, so here's a quiz for you. See if you can extend this circuit to be a 3-input NAND gate if you had A, B, and C coming in the inputs. I'll let you think about that. If you want to, of course, you can look at the slides available on the wiki.